Alrighty then, so last we spoke long ago on Wednesday, we had, as a reminder, determined that for the equivalent one-body problem, we can correctly get the actual energy of the two-body problem by using the quantities that are relevant to the one-body problem. The equivalent one-body problem, that the energy of the system, the kinetic energy is 1/2 mu v squared, where mu is the reduced mass and v is its velocity, which is how fast, or it's the velocity of mass 2 relative to mass 1 in the real system, and then minus gm mu over r. So take the combined mass of the system, capital M, and the reduced mass mu, multiply them together. That's the same thing as M1, M2. And so the gravitational potential, the total energy looks like you would expect for a reduced mass mu orbiting a fixed mass m and having their gravitational potential energy being given by that. It gives you the right result that applies to the actual two-body problem. And now we're going to show that we get a similar sort of thing for the angular momentum of the system, the orbital angular momentum. But first I will point out, how many of you have already had mechanics, physics 310, right? Okay, a lot of you have then, yeah. You have not, but that's okay. Then you can just look at this and smile and not have to really think much of it. But if you've had mechanics already, then I will say, note that the Lagrangian, right, remember the Lagrangian, L equals the kinetic energy minus the potential energy. I'll call it T here because you often, did you call it K or T in mechanics? Yeah, so somehow T gets mechanical, kinetic energy becomes T in mechanics classes for some reason. Now was the potential energy V or U?
I think it was U as well.
Was it U? Or yeah, okay, so okay, T minus U, cool. Okay, T minus U, well that would be, okay, the kinetic energy is 1/2 mu v squared, and now we subtract the gravitational potential energy, so it would be plus gm mu over r. Gm mu over r. So if you wanted to do it in Cartesian coordinates, you'd be writing 1/2 mu x dot squared plus y dot squared plus z dot squared plus gm mu over square root of x squared plus y squared plus z squared. I have a righto in my notes as opposed to a typo. I forgot to put the square root in there. Equals, well, if we do this in polar coordinates, because that's the natural thing to do, is to use plain polar coordinates here. That would be 1/2 mu, and then you'd have, so do you remember in polar coordinates, what are the components of the velocity? And I'll mention this anyway, because even though we're not going to be using the Lagrangian here, this bit is relevant to us. So if I'm working in polar coordinates, right, so I'll put up a background Cartesian coordinate system. There's m, here is mu, and it has some velocity v, and I want to resolve it into its radial and tangential components. So here's r hat, here's theta hat. Does that look familiar? Like r hat, theta hat when you go into polar coordinates. Do you remember? So v is equal to what times r hat plus what times theta hat. What's the, so the position coordinates are r of t and theta of t. So what do you get for the radial velocity component? So in other words, if I say v sub r hat plus v sub theta hat, but what are those in terms of polar coordinates? It's what r hat plus what theta hat. what is V sub r in terms of r dot and theta dot? What is V sub r in terms of r dot and theta dot? Crickets. 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 So it's just r dot, dr dt, the rate of change of r with respect to time. How fast is it moving away from the origin? It's just, well, r is the distance from the origin. Theta is angle away from whatever you've picked to be the x-axis. So dr dt is just the radial component of the velocity. Does that make sense, or does that not make sense? Dr dt, the rate of change of r is how fast it's moving inwards or outwards. If dr dt is positive, Vr is positive. If dr dt is negative, Vr is negative. It's moving inwards. Does that make sense? Happy? Not? I'm not seeing a lot of happiness here. I can't tell. You just don't look happy. Yeah. Yeah. Or you just like, yeah, whatever. What's that? It's quite all right. No, I want to know if people are puzzled by this. I really do. So what if it were only moving in the r direction? If it were only moving in the r direction, then just like if it was only moving in the x direction, what's the x component of its velocity? X dot, right? dx dt. If it's only moving in the r direction, same deal. R dot, dr dt, is how fast it's moving in the r direction. If it's not only moving in the r direction, that's still the component in the r hat direction of how fast it's moving is dr dt. Now, for v sub theta, so if I resolve, if I kind of draw it bigger here, so here is r hat, here is theta hat, here is v. If I resolve v into a radial component and a tangential component, a theta direction component, if I resolve it into those two components, so I could also draw a v sub r, a v sub theta, and a v sub r in those directions. Again, v sub r is just r dot. V sub theta is a little trickier. It's not theta dot. Notice that doesn't have the right units, right? Theta is dimensionless, it's radians. So theta dot is inverse seconds. But if I want to turn that into meters per second or whatnot, you have to look at it like this. So if it makes a little displacement, so here's x, y, good enough, and if my particle makes a little displacement, so here's theta, here is d theta, a little increment d theta in angle there, and I want to know this component right here, that component, how far did it move? So if I look at this as like dr, the change in the position vector going from here to here, okay, then dr is, and it's funny notation, dr r hat. In other words, here dr is not the magnitude of dr, the vector. Dr is the change in the radial coordinate. Dr is dr r hat. What about this piece right here? Well, what is this distance? What is that distance right there if we've turned through an angle d theta, a distance r from the origin? What is that distance right there from the small angle approximation? It is clear that I need to remind you or go over this of how this works. Yes?
D theta.
Not just d theta. So d theta is the change in angle, but I want to know what distance it went. So if I was further away, that same change in angle would be a bigger distance. So
Sine theta.
not that either, actually. Not that either. So if I draw a circle, here's a circle, and the radius of the circle is r, and this angle right here is, let's call it phi. What is that arc length right there? It's r phi, right? Remember that the definition of angle is phi in radians by definition would be this arc length. If I called this arc length right here s, if I called that arc length s, by definition, that angle phi is s divided by r, that angle phi in radians. That's the definition. If phi was all the way around, if phi were all the way around, what would s be equal to? No, don't, you're being too fancy here. So in other words, if I go all the way around the circle, what would s be? If the circle's radius r, if I go all the way around, I've just done the circumference of the entire circle. What's the circumference of a circle in terms of its radius?
2 pi r.
2 pi r, right? So if phi is all the way around, then phi would be 2 pi r over r, or in other words, 2 pi. In other words, there are 2 pi radians in a full circle, right? That's the point there. 2 pi radians in a full circle. The definition of radian angle is that if you put the angle at the center of a circle of radius r, then the arc length that it cuts off divided by the radius is that angle. That's the definition of radian angle. Go all the way around, you've gone 2 pi r, and so all the way around is 2 pi radians, and any other angle is some fraction of that. So let's apply that here. This is a straight line, but as long as d phi is, as long as my d theta here is small, that straight line is a pretty good approximation to a little arc of a circle there. So apply this result. If phi is s over r, then s is r phi, s is r times phi. Okay, apply that to here. This little arc right here is going to be the radius of the circle times what is playing the role of phi here?
R d theta.
R d theta, yeah. This is r d theta. And so dr, this little vector right here, can be broken into components in the limit that the displacement goes to 0 in that limit, into a component dr in the r hat direction and r d theta in the theta hat direction. So dr, the vector, is dr r hat plus r d theta theta hat. V is what? What is V equal to? If that's dr there, and it happened in time dt, a little time dt, what is V?
dr over dt.
Yeah, it's dr over dt, right? Dr over dt. V is dr over dt, which in the limit that dt shrinks to 0 becomes literally the derivative of dr dt, right? The derivative of r with respect to t. Well, that's going to be dr r hat plus r d theta theta hat over dt, or in other words, it's dr dt r hat plus r d theta dt theta hat, but we call dr dt r dot, and we call d theta dt theta dot. So in other words, over here, it's that V is r dot r hat plus r theta dot theta hat. So in other words, V sub r is r dot, and V sub theta is r theta dot, which shows up in the homework. That's the second problem in the homework, where you're finding VR and V theta for an elliptical orbit. And so in the homework, I just state that V theta is R theta dot. This is why. This is where that comes from. That's, I didn't just give that to you thinking just take it for granted. You should understand a derivation like this. This should be in your head of how this works, because this just shows up all the time in physics and in astrophysics. So at this point I say, what questions do you have? Well, you should be able to do this, you should be able to make this drawing and come up with this whenever you need to in order to get those components like that. That should become intuitive for you. Are you thinking of raising your hand, or are you just pondering, or just pondering? Okay, cool. Okay, all right. So V squared, like any self-respecting vector, and even ones that don't respect themselves, is the sum of the squares of the two components. So V squared is VR squared plus V theta squared, or in other words, it's R dot squared plus R squared theta dot squared. And so if we're writing the Lagrangian, and our generalized coordinates are the polar coordinates R and theta, we're using those as the generalized coordinates, then when we're writing the Lagrangian, in terms of R and theta, the generalized coordinates, it would be 1/2 mu R dot squared plus R squared theta dot squared, and then minus g m mu over r. So here is L of R theta, R dot, theta dot. There's your Lagrangian. And all the mechanics follows from applying the Lagrange equations to that. So from which all the physics follows. We're not going to do that here, but I just wanted to point it out if you've had 310 already, mechanics, and if you haven't, it's still important that and even if you had, I wanted to go through this bit so that you see that VR is in fact R theta dot. Right, in other words, you do the d dt dl dr dot minus dl dr is equal to 0, all that business, and then that would give you the equations of motion, in other words. Okay? What questions do you have? Comments, observations? You feel like, it looks like you're going to say something. It would be fine. It would be fine if you had a question. Okay, all right. Okay, sort of back to our story. Can I erase this yet, or is people still writing that down? Can I do it? Okay, it's going, goodbye. Okay. For the system orbital angular momentum, we have, okay, remind me here, so if I have some origin and I have some particle of mass m, and it has momentum vector p, then here is its position vector that connects it to the origin. There is its momentum vector p. Its angular momentum around the origin is given by what expression? So here's this particle, mass m, momentum p, position vector r from the origin. What is its angular momentum? Its orbital angular momentum. Its angular momentum due not to spinning on its own axis, but due to its motion through space in bulk. It's
P cross R.
oh, so close.
Cross P.
It's R cross P. It's R cross P, yes. Because remember, P cross R would be minus R cross P. So it's R cross P is how, we could have defined it as P cross R. That worked just as fine. But we made it R cross P. Yeah, so it's R cross P. Its angular momentum is R cross P. That's the definition of its angular momentum. So, with respect to our origin, whatever it is, L will be, so of course, another way to put this is it's R cross mv, right? Because P is mv in classical mechanics. And of course, you're free to pull the m over here, so it's also m times r cross v. So the total angular momentum of our two bodies will be m1 r1 cross v1 plus m2 r2 cross v2. But from earlier, we found that, so this is a reminder, you can go back in your notes and see this, m1 r1 is equal to minus m1 m2 over m1 plus m2 times r, where r was the relative vector r2 minus r1, was equal to then minus mu r, and also m2 r2 in the two-body problem was equal to mu times r in the equivalent one-body problem. And again, remember, r is the vector that connects mass 1 to mass 2. That's r at all times. So we can say that L is, we'll put in that m1r1 is minus mu r, m2r2 is mu r, so L is equal to minus mu r cross v1 plus mu r cross v2, just putting in those results, that m1r1 is minus mu r, and m2r2 is plus mu r. But that's equal to mu r cross v2 minus v1. I can do that with a cross product. I can factor it, just like I would factor ordinary numbers. So I can pull out the mu r cross v2 minus v1. In terms of the equivalent one-body problem, what is v2 minus v1? So r, remember, and so you need to be reviewing these. Right? Don't just do this during class. You have to review afterwards to be sure that you understand what everything means. Otherwise, you just get more and more lost. So R is R2 minus R1. R is R2 minus R1. Yes?
But isn't that the same as R2 minus R1?
Not quite. So R is R2 minus R1. V is R dot. Yes. Yeah. Equals R2 dot minus R1 dot. So in other words, what we find is that V is V2 minus V1. V is the relative velocity of mass 2 relative to mass 1. It's the velocity of mass 2 that you would see if you were riding along on mass 1. So V2 minus V1 is the relative velocity V, right? And it's important to keep those definitions in mind. R is the relative position. It's where mass 2 is relative to mass 1. V is the relative velocity. It's the velocity of mass 2 relative to mass 1. That's so important, I'm going to write it again here. R equals R2 minus R1 is the relative displacement. It's how far away your mom and dad are. The relative displacement, and your cousins and all that. And your siblings. The relative displacement, i.e., the displacement of mass 2 from mass 1. The displacement vector of M2 relative to mass 1, relative to M1. And so V is the same thing with velocity. I'll just write it over here because I'm running out of room over there. V equals V2 minus V1 is the relative velocity. The velocity vector of V2 of M2 relative to M1. Or in other words, how you would see M2 moving if you were riding along on M1. Questions, comments, observations? So this is what gets the box. L is mu r cross V. So the grand high conclusion is L is mu r cross V equals r cross P where P equals mu V is the momentum we would assign to the reduced mass. So be sure you understand the significance of this, right? Before we'd said that if I have a single mass m and it has some momentum p equals mv and its position vector at some moment relative to our fixed origin is r, then we would say that L was equal to r cross p equals r cross mv. And the point is, we are saying that in our equivalent one-body problem, which isn't the actual system, it's M1 and M2 is the actual system, but we're getting away with turning the actual system into equivalent single-body problem. We're saying that here's mass mu, moving with momentum P equals mu V with position vector R. We're saying it's exactly the same formula, L, that for the two-body system, that's the significance here, for the two-body system, we can get its total angular momentum from exactly the same formula that we do for a single particle moving with velocity v. Here, we've got a single particle of a reduced mass mu moving with the relative velocity v at the relative displacement r from capital M in the equivalent one-body problem. That's why it's an equivalent one-body problem, because using what you would think was the formula for the energy on the one-body problem, you get the correct energy for the two-body problem. Using what you would think is the formula for the angular momentum for the equivalent one-body problem gives you the actual sum of the angular momenta of the two bodies in the two-body problem. But it's easier to do a one-body problem than it is to do a two-body problem, which is why we bother doing all this. What questions do you have? So be sure you understand the significance of this. And if you don't, let me know. Yes?
This is only with reduced mass?
I'm sorry?
This is only with reduced mass?
So the idea is that we've really got M1 and M2. And really, if we want, we've really got M1 and M2 orbiting their common center of mass. And we could, in principle, do everything to keeping separate track of M1 and M2 and adding up their angular momenta, et cetera, where we would say the total angular momentum is M1 R1 cross V1 plus M2 R2 cross V2. The great thing is that if we define this equivalent one-body problem, where we define mu to be M1 M2 over M1 plus M2 for any one-body, for any two-body problem gravitationally, we can define the equivalent one-body problem. What's the reduced mass we should use? It's always M1 M2 over M1 plus M2. What's the value of capital M in our equivalent one-body problem? It's always M1 plus M2. So there's a direct formula for deducing the equivalent one-body problem. When we do that, the angular momentum of the reduced mass in the one-body problem is equal to the sum of the angular momenta of M1 and M2 in the actual two-body problem. But it's an easier calculation to study mu moving around and then turn it into what it would be for M1 and what it would be for M2 if we need to, using our formulas that I've erased now, but that M1R basically we have these formulas that tell us R1 and R2 and V1 and V2 in terms of R and V from the one-body problem. I don't know if that answered your question, but that's my long-winded answer, hoping that somewhere in there I was answering what you were wondering about. What other questions do you have? And all this is very important to astronomers. I'll remind you, so why are we doing all this? Binary stars, for example, right? We can't put stars on scales, so, but what we can do is observe stars orbiting one another and deduce their orbiter parameters and calculate their masses from Kepler's laws, from Kepler's third law applied to the two bodies, and Kepler's second law. We can, and so that's why this is so significant. This is the only way we have of determining stars' masses is from their orbital dynamics. And this greatly simplifies that is what it comes down to, the equivalent one-body problem. And it's cool just mathematically speaking. I will note P is the momentum we would assign to the reduced mass. Is P the total momentum of M1 and M2 in the actual system?
It's up there, center of mass of the system.
So if we're in the center of mass frame, if we're riding along on the center of mass, what is true about the momenta of the two bodies in the center of mass frame? So remember this, that the total system momentum, P, we proved is equal to the system mass times the velocity of the center of mass, right? So if we're in the center of mass frame, where the center of mass is stationary at the origin, what is the velocity of the center of mass in that frame? So what is the total momentum in that frame? Right. So if we're riding along with the center of mass, if we're in the center of mass frame, then the system momentum is 0. The two bodies have equal and opposite momenta. So P is the momentum we would assign to the reduced mass. Be careful and realize that's not the system momentum here. The system momentum is 0. Right? So this is not the system momentum in the C of M frame, that is P is equal to 0. So that's why I say it's the momentum we would assign to the reduced mass. It doesn't represent the momentum of the system. It represents a convenient calculational tool to get the angular momentum of the system. So there are some differences between the one-body problem and the two-body problem that you have to keep in mind. Not every time you draw a symbol, not every time you write down a symbol in the one-body problem does it directly correspond to the same thing, quote unquote, in the two-body problem. Okay? Happy, not happy? Ready to move on? Let's move on. Okay? So, we will do the start of the derivation of Kepler's first law. I say start because I don't want to spend the time in class that it would take to go through the entire proof. It's in the notes, it's in the book, so have a look at your own time. It's very worthwhile, but I don't want to spend an entire half period in the class going through the proof. I could go through it faster than that if I wanted, but you'd probably be like, what? So it won't take you that long to read through it. But this is going to be, I'll start it, and then I'll say, okay, and then look at it later. You know, if you're interested in the details of how do you prove this, it's cool that you can. Go ahead and do so. The point here is that Kepler came up with the what. Kepler said what of orbital motion? That the bodies orbit on ellipses, that the equal areas and equal times, and p squared equals a cubed in the right units, all that business. Newton came along, and with his laws of motion in particular, the net force on an object is equal to its rate of change of momentum, coupled with his Newtonian law of gravity. The force is g, product of the masses divided by the separation squared between them. With those two things, he was able to show that Kepler's laws follow, that Kepler's laws are a consequence of Newton's laws of motion and gravity. And so that produces a more fundamental understanding. So Newton came along and gave the why. Now, of course, whenever we come up with a breakthrough in physics like that, it tends to just push the questions further back. In other words, okay, now we know why Kepler's laws apply. Why do Newton's laws apply? That's you know, there's always a metaphysical question, right? We can figure out what the laws of physics are. Answering why they are the way they are, well, that's trickier. String theorists would like to try to do that. It hasn't worked so far. But in other words, okay, now we'll have explained Kepler's laws in terms of Newton's laws, but where'd those come from? And of course, Newton's laws, are they exactly correct? Or have they been superseded by more fundamental physics? God, it's hot in here. You notice that? There's too much, yeah. I'm always cold in my office, and then this room is way too hot. But anyway, where was I? Is Newton's second law, is force really equal to, well, okay, is F really equal to ma?
Yeah.
No, it isn't. It is not. In Newtonian physics it is, but Newtonian physics has been superseded by somebody else came along and gave us something better. Who was that somebody? Starts with an E. Einstein, right? So in relativity, it's still true that force equals rate of change of momentum, but momentum isn't mv, and so force isn't ma, right? So, and then also, is Newton's law of gravity our current description of how gravity works? No, what is our current description of how gravity works? General relativity, also from Einstein, yes. So Newton's laws are just approximations. They're not strictly speaking correct. But are they valid? Yes, because they're still super useful under a wide range of conditions. But we now know of conditions in which they don't work well anymore. So keep that in mind too. Anyway, the beginning of a derivation of Kepler's first law. What's Kepler's first law say again? What's that one? That's the one that says the orbit. That's the second law.
Ellipse.
It's an ellipse, yes. First law is the one that says the orbit is an ellipse. Kepler said with the sun at one focus. Now we know better. What really happens if you got two bodies in orbit, it's not that the sun's at one focus, it's not that the larger of them is at one focus. What's at one focus of their two elliptical orbits? The center of mass, yes. The center of mass of the system lies at one focus of the elliptical orbits of the two bodies. That's the actual law. So, except when you do general relativity and it turns out, okay, no, the ellipses are not, it's not quite the right solution. Even, you may know that the detection that of the perihelion precession of the perihelion of Mercury's orbit was the first really good evidence for general relativity, because general relativity predicts that an ellipse is a good approximation to the orbit, but that the semi-major axis doesn't stay fixed in space, or the major axis doesn't stay fixed in space. It slowly moves around. And that had been detected before Einstein came along for Mercury's orbit. There was so you would already predict from the interaction of Mercury with the gravity of the other planets that the orientation of its major axis should slowly shift around the orbit. But there was an excess over and above that predicted from Newtonian physics of about 43, if I recall correctly, arc seconds per century. Tiny angle, but they had good enough observations in the 1800s to detect this excess precession of about 43 arc seconds per century. And Einstein, when he was developing general relativity, found that his theory predicted that it would account for that extra additional precession of the perihelion of Mercury's orbit, of the orientation of the major axis of Mercury's orbit. So that just, Einstein apparently was just, practically dancing a jig when his calculations showed that, hey, I can show why this is so. The beginning of a derivation of Kepler's first law. So we have, using our just obtained expression, L equals R cross P for the one-body problem, the equivalent one-body problem, we have, take a derivative. dl dt is equal to, okay, if I take the derivative of R cross P, if I take d dt of R cross P, it's a product. It's a cross product, but it's a product. And the product rule of derivatives does apply to a cross product. We just have to be sure to not change any orders, because cross product, remember, order matters. If you reverse the order, you change the sign. So dl dt will be derivative of the first cross the second plus the first cross the derivative of the second. And it's okay to switch those two terms that are added together there. What you couldn't do is flip the roles of P and R. You can't turn those around. So dl dt is dr dt cross P plus R cross dp dt. What's another name for dr dt? Yes? It is, but I want a single simple symbol. Yes, V, yeah, just V, right? So this is V cross P. So you're not wrong, but V cross P plus R cross, and it turns out that the equivalent one-body problem, this is legit. What is dp dt? Newton's second law says dp dt is
Force.
the force, yeah. So this is R cross F. The force on the reduced mass is the same as the force of either of the two bodies on one another in the real problem, so to speak. So we have V cross P plus R cross F. So I say this is equal to 0. Why would that be? How are P and V oriented with respect to one another? Yes? They're parallel, yeah, they're parallel, right? Because P is just mu V, right? So they are in the same direction. And if I cross two parallel vectors, what happens? It's 0, right? It's 0 because the two vectors are parallel to one another, equals 0, since V is parallel to P, so I'm using two vertical parallel lines to mean is parallel to. V is parallel to P, so that cross product is always 0, right? Because it's, you know, in magnitude, it's the magnitude of the first times the magnitude of the second times the sine of the angle between them, but the angle between them is 0 here, so sine of 0 is 0, so 0, okay? And then here we've got R cross F. And the point with this one is here is M, here is mu, here is R that connects M to mu. What is the direction of the force on mu due to gravity? Which way does it point? Could it be, say, off in this direction? The gravitational force due to M on mu, could it be like this? Could it be like this? What way does it point? How does gravity work?
Towards big M.
Towards big M, yeah. Gravity is a mutual attraction, right? Towards big M. It's a central force. The force of gravity between two objects in Newton's theory is along the line joining their centers and towards one another. So F, the gravitational force, and R are 180 degrees apart, right? R points from M to mu, F points from mu to M. The force on mu is what we're interested in here, points from mu to M. And so R cross F should be equal to what, given that those two forces are 180 degrees apart in direction? Also 0. Also 0, since R and F are anti-parallel. 180 degrees away from one another. They're anti-parallel. So dl dt is equal to 0 right before the break, which Kayla is dutifully staying here until, even though she's going to go all the way to Sanborn in a few minutes here. What does that say about L? If its derivative is 0, L itself is constant. L is constant. L is constant. In other words, it's conserved. L is a conserved quantity. It stays constant. It's time for a break. Let's take a break, shall we? Should we consider moving to room 130 because it's freaking hot in here, or should we just stick around in here? What's that? You think it's okay in here? Yeah. I mean, if everybody's okay in here, if you're like, you know, I don't want to move, I'm fine with that too. Really? Wow. Hey, I mean, there will come a time in the winter where this will be delightful to me, but we are not there yet. This is not delighting me. But no sacrifice too great in the name of science education. So, woo, let's go here. Let's do this. All right. So, L is constant. And note this will be true for any central force law, right? Because if you've got that R is along the same direction as F, then there's no torque, is what it comes down to. The gravity doesn't produce a torque. It just tends to produce, you know, the force will slow it up or speed it up or slow it down in the radial direction, but it's not exerting any torque. And so that doesn't mean you can't be moving sideways, but gravity's not, you know, producing a torque. So this holds that L is constant for any central force motion. And it has a very important and fundamental consequence. Namely, that the orbit is a plane. If you have two bodies, they orbit one another in a single plane because gravity isn't doing anything to pull either body out of that plane. So, L is R cross P, and a cross product is perpendicular to both vectors in the cross product, right? That's the way cross products work. So this says that R is perpendicular to L. That's my way of saying is perpendicular to. R is perpendicular to L. And so this says the orbit lies in the plane perpendicular to L. So the orbit lies in the plane perpendicular to L, because L's constant, right? L's just this constant vector. The orbit lies in the plane perpendicular to L. Why, that is eminently box-worthy. Draw a fancy schmancy picture here. Here's the orbit. Here's the plane of the orbit. There's the reduced mass on its merry way orbiting along that orbit there. And here is the L vector that is perpendicular to the plane of the orbit. So if you have two bodies orbiting one another, they orbit in a single plane. That plane could have any orientation whatsoever, but it is a single plane that they remain in at all times, which kind of makes sense because gravity is along the line joining them, so there's no force up or down relative to the plane. There's nothing pulling it out of the plane, is what it comes down to. Now, blah, 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 math, vectors, blah. In other words, pages 9A and 9B of my notes. Because remember I said we were going to start the proof of Kepler's first law. Well, this is a super important thing to know. And then I go on, or the book goes on, and we finally obtain the following. We finally obtain this glorious result. That from F equals dp dt, and that force is the gravitational force, it follows that the orbit has the following equation. R is equal to L squared divided by mu squared over gm times 1 plus e cos theta. Again, for the details, see the notes or see the book. We obtained that result right there. So that is r as a function of theta for the orbit. In other words, y there is the equation of the orbit in polar coordinates, and you might vaguely remember that we found the equation of an ellipse in polar coordinates, and lo and behold, it had something over 1 plus e cosine theta in it. In other words, we have shown that the orbits are, more general than that, conic sections. This is the equation for a conic section. So this says, the orbit is a conic section. So, Halley asked Newton, can you prove that the orbits should be ellipses? And Newton said, I'll work on that. Yeah, I can do that because I'm Isaac Newton. So the orbit is a conic section. Bang, the orbit is a conic section. Let's write down the equations in polar coordinates of all the different conic sections. For conic sections, what we have is, for an ellipse, as we've already met, for an ellipse, r is equal to a times 1 minus e squared over 1 plus e cos theta. So in other words, L squared over mu squared gm is equal to a times 1 minus e squared if the orbit's an ellipse, right? Just identifying in those two formulas there. So why this works as the equation of an ellipse, and this has 0 is less than or equal to e is less than 1. It's for that range of the parameter e that you've got an ellipse. But you can also have a hyperbola, or as I called it when I was a kid and saw it for the first time, a hyperbola. I mean, it looked plausible to me, hyperbola. Had a hyperbola and a parabola. Nope, not so. But anyway, a hyperbola, why that would be r is equal to a times e squared minus 1 over 1 plus e cos theta. So notice the only change is instead of 1 minus e squared, it's e squared minus 1. And that applies for e greater than 1. For e greater than 1, that's the equation. And then there's the parabola, the parabola, which is, as we mentioned before, right on the border. For a parabola, it turns out that r is equal to 2p over 1 plus e cos theta. But in this case, e is equal to 1, and so I just wrote it there for completeness. In other words, it's 2p over 1 plus cos theta. Well, it's also 1 plus e cos theta, as long as I remember that e is equal to 1 there. So that's just that special particular case. So you can match up, right? In other words, L squared over mu squared GM is equal to the appropriate denominator stuff in all those various situations. Glorious! And then we're going to come up with an equation here, which is going to be, this is going to be so much your friend when you're doing some of the homework problems. It's going to be like, oh, I just got to come back to this all the time. Like if maybe Jupiter's orbiting the sun and I knew its semi-major axis and I knew the sun and Jupiter's mass so I could find mu, and I wanted to answer, say, like, you know, what is the orbital angular momentum of the Sun-Jupiter system? Why, you would want to use this formula right here. So, for an ellipse, taking this to heart, for an ellipse, this says that A times 1 minus E squared over 1 plus E cos theta is equal to L squared over mu squared over GM 1 plus E cos theta. Solve for L. Solve for L, and what do you get? Why, you get that L is mu times the square root of GM times A times 1 minus E squared. Hello, friend. Hello, friend. You are going to want to keep that in mind when you're doing a problem that might, for example, be about Jupiter orbiting the sun, you know. Well, really, of course, Jupiter doesn't orbit the sun. Jupiter and the sun both orbit the solar system barycenter, but you know what I mean. So, hello, friend. Super useful formula. What questions do you have? Yes?
This is kind of going back several minutes.
That's fine. Yeah.
So if everything orbits like the center of mass on a plane, how much like wiggle room does it have to go off the plane? Like what like margin of error is, how flat is it at?
So if you have just two bodies and they are isolated, in other words, there's nothing else in the universe exerting a force on them, then mathematically speaking, it's a perfect plane, razor sharp. There's nothing about them deviating at all. Now, that plane, again, could in principle have any orientation in space that you like, and in our solar system, the orbital planes of the planets are nearly the same as one another, but not exactly the same as one another. And furthermore, if we just stick to Newtonian gravity, they're all tugging on one another gravitationally. And so that means that they can exchange angular momentum with one another. The total angular momentum of the solar system stays constant, but one planet could give some of its angular momentum to another planet. And so, because of the fact that they're tugging on one another, that it's not, our solar system is not a two-body problem, it's a more than two-body problem, then the orbital planes of the planets can slowly change a bit over time. But if it were just two bodies, then no, rigidly locked into place. It's a plane, and that's just all there is to it. Yep. Okay. We will find later that our sun and solar system orbiting the center of our galaxy moves, it has an up and down bobbing motion as it orbits the center of the galaxy, because our motion is tilted a little bit relative to the galactic plane, and so when it rises above the plane's saying, whoa, whoa, get back here, get back here. And when it goes below the plane's saying, whoa, whoa, get back here. And so it undergoes an oscillation up and down, above and below the plane of the galactic disk, for example, and all the other stars do things like that too. So things can certainly get all complexicated, so to speak, but for a two-body problem, simple as could be, it's a plane, and don't you worry about anything else. Yep, okay? So, that's Kepler's first law, with a lot of mumble, mumble, blah, 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 right? Again, you can go and see the details on your own later. Now we are going to do it upright and really derive Kepler's second law, the law of equal areas. And by the way, if you look at my notes, so a lot of my notes I wrote with the first edition of the textbook, which didn't have this proof of Kepler's first law in it. And then the second edition came out and it did, and I thought, cool, I should put that in there. This is why my pages go from 9 to 9A to 9B to 10. 9A and 9B are pages I inserted in order to include the proof of Kepler's first law that showed up in the second edition. I'm like, oh, I got to do this. I got to put these in my notes too. So if you're following my notes at home, so to speak, you're like, why is it going 9A, 9B? That is the reason. So now let's prove Kepler's second law. Where do I start that here? Yeah. So derivation of Kepler's second law starts at the bottom of page 9, and then you leap to page 10, because 9A and 9B are first law. Or you just follow the notes that you're taking here, either way. But just in case you want to cross-correlate and all that. So, derivation of Kepler's second law. So wait, which one's the second law? We said it earlier. That's the one that says equal areas and equal times. And we'll see it's a consequence of angular momentum conservation. That the rate at which area is swept is proportional to the orbital angular momentum, but the orbital angular momentum is constant, so therefore the rate at which area is swept is constant, therefore equal areas and equal times. All right? So, derivation of Kepler's second law. The equal area law here. So, at its heart, as I just mentioned, let's see. Shoot, I was looking for like some red chalk so I could fill it in, you know, being a little heart there. But at its heart, it is a statement of conservation of angular momentum. I just feel so motivated to, it just seems right. And I feel like there's probably a little red piece of chalk in here. These are the things that, you know, I stay up at night worrying about. So, what do we got here? There we go. Here we go. I got it. Here, isn't that nice? I like that. Okay. So, from above, so let's see, L is equal to R cross P. So that says that, oh, wait a minute. No. This is from, I was about to just say the same thing we did before about the L being conserved. This is me like, oh, there's my old notes, and then I did them again in the new notes that I inserted. So, all right. Back to our story, page 10 here. So, from above, we know L dot is equal to 0, and L equals constant. It's a constant. So let's draw a section of the relative orbit in the equivalent one-body problem. And we'll say, okay, let's have mu go between these two nearby points on the orbit. And this will be one of those deals where we're considering the limit as they get infinitely close to one another, but I'm drawing them a nice finite distance apart so you can see what I'm doing here. So here is d theta, because remember we talked about theta, the angle away from perihelion, to track where the particle is. So there's d theta, and here is r. And so, actually, I'll probably draw it over here. Here's r. Here's, what's this distance right there? That little piece right there. If that's r and that's d theta, that little perpendicular projection right there, that's going to be?
RD theta.
Yes, there we go. RD theta. That's RD theta right there. RD theta. That's RD theta. Just blurt it out, right? I know you're like, what if I'm wrong? Everybody's going to like, nah, just blurt it out. It's cash here. The least I can do is say, oh my God, how stupid are you? Except I won't do that. It'll be fine, right? So don't worry, it's fine. RD theta. A section of the orbit. Section of the orbit. Wow. What? A section of the orbit looks like a skinny triangle. With area dA, so that's just to say that's a little area there, equals 1/2 times base times height, right? So that's the formula for the area of a triangle. So that'll be 1/2 times, we can say like the base is r, RD theta I mean, and the height is r. So in other words, it's 1/2 times RD theta times r. And the smaller d theta is, the closer this comes to just being just like this little segment of the arc with a little triangle there and all that. So in other words, again, I'm really talking about this whole area as being dA, and the, well, no, actually, I got that wrong. I'm thinking of the wrong direction in terms of basis height. So in other words, I'm saying, and that's why I did that. Okay, I'm going to make that r right there. The lower one is r, so then r is the base of my skinny triangle, and RD theta is the height, right? So that's the height is RD theta, and r is the base of my skinny triangle. So this is really an arc of the ellipse, so it's not really a straight line, so it's not really a triangle, but the smaller d theta is, the closer it comes to being true that that little tiny arc section is practically a straight line. And so in that limit, I can say the area of this triangle is 1/2 base, which is r, times height, which is RD theta. So dA is equal to 1/2 times RD theta, or in other words, it's equal to 1/2 r squared d theta. Make sense? Not make sense? What questions do you have? So 1/2 r squared d theta is dA. So dA dt, the rate at which area is being swept, dA dt, well, divide by dt here, and you get 1/2 r squared d theta dt. dA dt is 1/2 r squared d theta dt, also known as 1/2 r squared theta dot, right? Because that's what theta dot means, is d theta dt. And so now I'm going to draw another copy of my orbit. And I'm going to say, okay, here is mu at some point. There's mu. And I'm going to resolve its velocity into components. So its velocity will be tangent to the orbit, right? It's locally tangent to the orbit. And so v at that moment, the full velocity vector v looks something like that. And I can resolve it into components along the direction to the focus and perpendicular to it. So I will resolve v into components Vr, the radial component, and v theta, the tangential component, like so. As noted previously, right, at the start of class, we did a lot of song and dance about this. V is then Vr plus v theta, right? It's the sum of those two perpendicular vectors, which is Vr r hat plus v theta theta hat. They're magnitudes times unit vectors. Well, they could be algebraically plus or negative, so they're the components times the unit vectors. So r hat here points away always from the origin in polar coordinates. So there's r hat, and theta hat is a unit vector in the direction of increasing theta. So there's theta hat. And we said, let's see, Vr was, in terms of r and theta, Vr, the radial component is Vr is what am I saying? Vr is it's a derivative with respect to time of what quantity? It's r dot. Yes, it's r dot. That's what I'm looking for. Yes, Vr is r dot, r hat, and v theta was r theta dot. Yes, r theta dot. See what happens when you just blurt it out, figuring, you know, right? See? So it's all right, yeah. Plus r theta dot theta hat. No guts, no glory, right? All right, r theta dot. So a dot is equal to, we said, 1/2 times r theta dot. I've just factored r squared into r times r. But in other words, well, what's r theta dot again? That's just v theta. So we can say that a dot is 1/2 r v theta. A dot, the rate at which area is swept, is 1/2 r v theta. 1/2 times how far it is away from the focus times its theta component of velocity, how fast it's moving perpendicular to the line of sight, to the focus, to the origin, to big M over there, right? In other words, here's big M, here's mu. So A dot is 1/2 r v theta. Now, the magnitude of r cross v, magnitude of the vector r cross v, will be the magnitude of, well, r cross v is r cross v is Vr plus v theta. And you can do the usual things. In other words, this is r cross VR plus r cross v theta. So the magnitude of r cross v is the magnitude of r, the vector r cross VR plus r cross v theta. That vector, because I've just expanded r cross VR plus v theta, because VR plus v theta is v. So if you feel the need to add that line in your notes before that line, then, wait a minute, what is r cross VR? What is r cross VR? So remember, r is the vector that connects m to mu. So this big long vector here, all the way from m to mu, that's r. How are it and VR related to one another? Yes?
R and VR.
Yeah, r and VR, because I'm taking r cross v sub r.
Parallel.
They're parallel, right? They're either in the same direction or opposite directions. VR could be outwards too. It's inwards in this particular drawing, but it doesn't have to be. Over here, it would be outwards. So what's their cross product? 0, yeah. So this is 0, since they're parallel, or anti-parallel. They're parallel, so they are anti-parentheses parallel, i.e. it could be either parallel or anti-parallel. That's 0. And so we get that r cross v in magnitude is r cross v theta in magnitude. Well, that'll be the magnitude of r times the magnitude of v theta times the sine of the angle between r and v theta. What's that angle? 90 degrees. What's the sine of 90 degrees? 1. So this is just rv theta, where when I don't put the arrow on it, it just means the magnitude of that quantity. It's just rv theta. So rv theta is equal to L divided by mu. Oh, I skipped a step. I went too quick. Okay, so rv theta. Can I erase all this stuff? Okay. I just didn't have the heart to erase the heart, so, okay. So, but L is equal to mu r cross v, so the magnitude of L is equal to mu times the magnitude of r cross v, but over here we showed that the magnitude of r cross v is rv theta. So this says that L, take off the arrow to just say how big it is, L is equal to mu rv theta. L is mu rv theta. And so we get what we were ultimately after here, that, and it's getting too small, that rv theta is L over mu. rv theta is L over mu, and thus we have Kepler's second law revisited. equal areas and equal times. Let's be more specific. What is the rate at which area is swept out? This says that A dot is equal to L over 2 mu. Since A dot is half RV theta, but RV theta is L over mu, so A dot is L over 2 mu. And we know since L is constant, that means A dot is constant. Well, that's the whole statement of Kepler's second law there, is that the rate at which area is swept out stays constant is the same thing as saying equal areas and equal times, right? Because A dot times delta T would be the total area swept out. And since A dot's a constant, in any two parts of the orbit, if the times are equal, the areas swept out are equal. So that's entirely equivalent to equal areas in equal times. But this lets us say how much area in a given amount of time. The area swept out is L over 2 mu times delta T, where delta T is the amount of time we're talking about here. So this is more specific. Can I erase this board here? Anybody want to stop me? I'm doing it. Okay. Glorious. So glorious. So Kepler's second law is really just angular momentum conservation. Should probably draw this again here, just to make it clear what's happening. So here's my orbit again. Let's see. So if we talk about, so I'll just use perihelion and aphelion. Turns out it's, I think I said aphelion before, and I looked it up because the Astronomy 111 textbook has some videos where they keep saying aphelion, and I'm like, pretty sure it's not aphelion, but maybe I've just been saying it wrong all this time. So I looked it up, and a bunch of people who pronounce it say aphelion. So it's actually aphelion. I think aphelion sounds better, but it's aphelion. Anyway, if I just generically use aphelion to be the near point and to be the far point and perihelion to be the near point, even if it's not orbiting the sun, then here is perihelion, here is over here on the other end of the long axis, the major axis, aphelion, and assuming it's orbiting, say, counterclockwise, then we can say there is the perihelion velocity vector, there is the aphelion velocity vector. Here is the position vector of perihelion. From there, here is the position vector of aphelion. And angular momentum conservation says that if I take those two cross products, they're equal to one another, right? Because mu r cross v is staying constant. So certainly this is saying it's moving faster at perihelion because r cross v has to be the same. And so if r is bigger, v is smaller, and vice versa. At perihelion and aphelion, it's like, hey, look, it's aphelion, right? Over there, there's aphelion right there. It's aphelion. But anyway, at perihelion and aphelion, r is perpendicular to the velocity, right? Because the velocity vector is tangent to the orbit at all locations. R is perpendicular to the velocity. So at these very special points, at these 2 points, L is just mu RV, right? It's normally mu r v theta, but here v theta is all the velocity there is. V theta is the component perpendicular to the line of sight. Well, here is moving perpendicular to the line of sight. So it's just mu r v theta. Y'all buying what I'm selling? You okay with what I'm saying here? So at perihelion, we get that our perihelion is, using the equation of the ellipse that we got from our derivation of Kepler's first law that we just threw, hand waved the result of. It's always true that r is L squared over mu squared times GM 1 plus E cos theta. But theta is angle away from perihelion. So in other words, at some arbitrary location, that angle right there is theta, right there. So at perihelion, what's the value of theta? If theta is angle away from perihelion, at perihelion, what is the value of theta? Yeah, 0. It's just 0. So it's going to be equal to, and I'll just put that in, 1 plus E cos 0, because it is 0 at perihelion. That's theta equals 0. So we put in, okay, at perihelion, L is mu RP squared VP squared. I'm sorry, L squared is mu squared RP squared VP squared at perihelion. So we get mu RP VP squared, because at any point you plug in, well, I'm sorry, what I was saying is at perihelion you'd plug in RP and VP, at aphelion you'd plug in RA and VA. They're equal, those products are equal because L is constant, so we get mu RP VP quantity squared over mu squared over, let's see, what's the cosine of 0? 1. Yeah, the cosine of 0 is 1. And so this becomes over GM times just 1 plus E. And so this turns into solve for VP squared. This turns into VP squared is equal to GM times 1 plus E over RP. When all is said and done, because here we've got an RP squared, divide through by RP, happily throw everything over to the other side. Those mu squareds cancel, and we're solving for VP squared. Okay, so throw everything to the other side, bring this RP over here to turn RP squared over RP into just RP. You get GM times 1 plus E over RP. But earlier we had found that RP is the semi-major axis times 1 minus E. So if you dig through the notes, you find that RP is the semi-major axis times 1 minus E. So in other words, VP squared is equal to GM over A times 1 plus E divided by 1 minus E. And that's also, whoops, squared. Let's say squared. That's also pretty box-worthy. That's a hello friend kind of equation there. And similarly, do the same analysis for aphelion. Similarly, we find that VA squared is equal to GM over A Well, if you had to guess, it's probably going to be pretty symmetric to this, except that instead of 1 plus e over 1 minus e, it flips over, 1 minus e over 1 plus e. So those are the perihelion and aphelion velocities. And hold those thoughts, because it would take me a little longer than the time remaining to get to the next thing I want to come up with. And so we'll come up with that next time. An expression for the energy in terms of the two masses and the semi-major axis. We will find the orbital energy only depends on A. It only depends on the semi-major axis of the orbit and not on the eccentricity of the orbit. And that has very profound consequences, as we shall see. We can use that to deduce, for example, that if you have a close binary star system, that tidal friction will dissipate energy in the system, but it can't dissipate angular momentum, and the result will be the conclusion that the orbit tends to become more circular over time. And we observe that close binary stars have circular orbits. Even if they started out with very elliptical orbits, over time tidal friction dissipates energy, and we'll see that causes it to reach the minimum energy orbit for a given angular momentum, which is circular orbits. So you get this very powerful statement out of this result, which we haven't come up with yet. So next time we'll come up with that result and be like, wow, we can get so much out of such a simple statement. Astrophysics is so cool. And you'll all just be like, you know, oh, this is just wonderful. But that'll be next time. So think of how you've got so much to look forward to right at the start of the next class. And then it's just going to get better from there. Alrighty, so see you next time.